This is you. You should get your calculators out so you can check me. I haven't actually done this. I just made this problem up earlier, and yeah, grab one. And if we're short, let me know because I've grabbed one myself, and I'll do the work as you do the work. See if I can. Oh no, not the timer. All right, try that. Oh, that looks terrible on my screen though. Okay. All right. Does this make any sense? Looking at this table that I've provided you? Yes, no. All right. So over the years, I've come to the conclusion that this is a helpful thing. So in the first unit, we dealt with this list of variables, and this is in the y dimension, so something that goes up and down and is in free fall, we could fill in whatever we have and we could solve for other things using the kinematics formulas. But now we're not just going to have things going in one dimension. This could have also been x, by the way. We're going to have things moving in the y dimension and the x dimension, and we can analyze them by looking at just the x dimension and using some formulas, using these formulas for the x dimension. We can look at just the y dimension, and then there's this overlap, like this angle and v. So we have v0y, v0x, and v0. All those are initial. This is the initial velocity. This is the x component of the initial velocity. This is the y component of the initial velocity. The kind of weird part is here I just have v0y, here I just have v0, here I have v0x equals vx equals average vx. What's going on there? And why is there no other stuff? It's because in the x dimension, so we'll be drawing another picture about like this in just a second. In the x dimension, going this way or this way, there's no gravity. There's no acceleration. So there is no acceleration in the x dimension for projectile problems ever. And the idea that the initial velocity and the final velocity and the average velocity could be different is ridiculous. If you don't have acceleration, they're all the same. So there's only one velocity. And there is no delta Vx because the x velocity never changes. Y velocity is going to change. It's going to go up, slow down, and then come down faster, just like we talked about. All right, enough of that. So the problem, you throw a ball that travels a horizontal distance of 80 meters, and it stays in the air for 4 seconds. And this is a weird assumption. Assuming the ball lands at the same height at which you released it, and assuming the ball is in free fall as it flies, then answer these 3 questions. So we want to find what was the speed of the ball in miles per hour when you threw it. That requires some new thinking. At what angle did you throw it, and how high did it go? So let's draw the ball here. Here's the ground, and just leave yourself out of it, but it's going to look something like this. And this is what I call a symmetric flight. So we're going to have 3 different kinds of projectile problems. Symmetric ones, where basically whatever happens at the beginning happens at the end kind of in reverse. And then we'll have asymmetric ones where it's going to start from here and then it's either going to land on a higher point or it's going to land on a lower point. Those are a little bit trickier. Did you get one of these, Gabe? You were here when okay. And then the third one is half. So usually it's going to be something like this. There's a car that's driving off of a cliff horizontally, and then it goes off the cliff and it flies down and lands in the valley below. So that's like half of a symmetric flight. It's going to go from the high point where it's traveling horizontally to the ground. This practice is just going to be the big normal symmetric one. We've got to figure out these 3 things, and I don't even want you to waste time thinking about those at the moment, because how to get to these is going to be kind of complicated. Guess what we're going to do? First step. Anybody? Do you know? Yeah, start filling stuff in up here. Okay. So let me readjust this thing. So we know the horizontal distance that it travels is 80 meters. Okay, what's that? That's something up here. Delta x. And let's, since I drew it going to the right, let's just assume that it is going to the right. So this is 80 meters. Positive 80 meters is the displacement. What else do we know? Time, 4 seconds. Now, as you know, you can be creative with this, and if it's helpful, and it might be in just a minute, like figuring out how high something goes, you don't want to use the total time. You want to use the time. You want to use the time to get to the top, and we may come back and do that, but for now, let's just use the total time and see what we can figure out. Come on, is it connected? Okay, good. All right. So, based on what we have right now, we can find something. And I'm just going to jump to it and tell you we can find this. We can find the x velocity. And in the x dimension, since there's no acceleration, you can use any of these formulas. You just put 0 in wherever there's acceleration. So this would become a really dumb formula. It would be v squared equals v0 squared. Basically, the ending velocity equals the starting velocity, which is true if there's no acceleration. This would be v equals v0, which is also true if there's no acceleration. This one, displacement equals v0 times t. That's true. That's basically this formula again, just rearranged. Displacement equals v times t. So if something travels 80 meters in 4 seconds and it's got a constant velocity the entire time, what's its velocity? 20 meters per second. And I think I'll just write, I don't know, I'll find somewhere to do this. I'm going to write average Vx. I could write Vx. I could write V0x. They're all the same thing. Equals delta x over delta t, and that is 80 meters over 4 seconds, and that's 20 meters per second. Okay. All right. Now there's something else we can fill in here that we left out. So acceleration in the y dimension, yes. What is the acceleration in the y dimension? Negative 9.8. So let's see. What should we do now? Time. We've got acceleration. Oh, what's delta y? We know this. Start here, in there. Delta y is what? 0. So, all right, delta y is 0. And there's a formula that has t and a and delta y and one other thing in it. Does anybody know what it is? I'll show it to you. It's this one, the displacement formula. So let's use that and see what we can get. So I'm going to write delta y equals v0y times t plus 1/2 a t squared. So delta y for this entire event, it starts at 0, it ends at 0. Delta y is 0. v0y, that's what we're about to find, times 4 seconds plus 1/2 times negative 9.8 meters per second squared times 4 seconds squared. So I'm going to skip a few little steps. You can watch me do it on my calculator if you want. But basically this part is, maybe you can't see that. I'm going to darken it a little bit again. If you want to go ahead and solve while I'm solving, you can solve that. So, I'll just do 0.5 times 9.8. I know it's negative, times 16. So I get 78.4. So this is negative 78.4. And I would subtract, I would basically move that to the other side. Both sides would be negative. I'm going to divide 78.4 by 4. And that gives me 19.6. Can somebody confirm, does that sound right for V0y? Everybody else done that? Okay. All right. So we know V0y is 19.6 meters per second. So now we know V0y and we know V0x. What can we find of these three things? We could find the initial speed. What else can we find? Not yet. I mean, we'll be able to do that in a minute, and we could do that now. But just from those two things together, we can find the speed and we can find the angle. So, what do I do if I know the initial x velocity and the initial y velocity, and I'm basically trying to find the initial velocity? How do I add those two? Like, how do I do it? Anybody know? Can you picture what I'm about to do? So, this is what I'm going to do. We've been doing this before. This is V0x, and V0x is 20 meters per second. And this is V0y. Wow, I didn't mean for it to turn out this way. 19.6 meters per second. What's the angle? Anybody? This component's 20, this is 19.6, which is basically 20. What's this angle going to be? 45, but we can just confirm. I'm going to do the inverse tangent of 19.6 over 20. Let's see, how do I do it on here? Second tangent, 19.6 divided by 20. 44.4. So this angle right here is 44.4 degrees, and that would be theta 0. Guess what else? If we know this, what else do we know? The final angle is also going to be 44.4 degrees because this is symmetric. Just like when we had things going up and down, everything was symmetric. Okay, so now we know I can put this angle in, 44.4 degrees above horizontal. So I've got an angle, and then I'm telling relative to what. How do we figure out the speed? How fast was it? So the x component, it was going to the right at 20 meters per second. It was going up at 19.6 meters per second. Yeah, it's the hypotenuse. So this would be the square root of the square, or the sum of the squares. So I'll just do 20. Oh, goodness. How do I do this on this calculator? 20 squared plus 19.6 squared. And then, oh crap! Somebody who's more savvy. What'd you get? 1184. That sounds really big. 28 sounds more reasonable. It should be basically this times root 2. So this times 1.414 is going to give us that. Can somebody confirm 28 point? Okay, 28 point what? 28. Okay, so V0 is 28 meters per second. So that is V0. Guess what V is? That's going to be negative. Well, that's going to be, let's call it 28 also. This is the tricky part. If we were going to say like V0y and Vy, then we want to do opposites. So Vy is going to be negative 19.6 meters per second. If it starts out going up at 19.6 meters per second, when it's over here, it's going to be coming down 19.6 meters per second. But over here, I've got, to express the direction of these, we've got these angles. So, I don't know. I really should say upward, above the horizon to the right, and this is like downward. I'd really need more words to do a good job there. All right, 9:15. We're closing in on time being up. So we've got these two, 28 meters per second. How do we figure out how high it went?
It's the same miles per hour.
Oh, yes. So this is something you've got to memorize. I forget which page of the packet it's on, but multiply it by 2.24. 2.24 miles per hour for every meter per second. I want you to know that conversion. 28 times 2.24. That's just one of the few things. So it's about 63 miles per hour. Can you throw a ball 63 miles per hour? Some of you might be able to. I don't think everybody in this class can. We could test it sometime. But back to this one. How high did it go? So of all these pieces of information, what's the one thing that's controlling how high it goes? What's that? What? There's just one particular variable that we need. Which initial velocity? The y velocity. The x velocity is irrelevant. This is irrelevant. This v0y right here, this is the one we need. So I'm just going to flip to the back because I've got a little bit of space. I'm just going to write 19.6 meters per second. And now remember when you're doing when you're trying to find out how high something goes, just look at half the trip. So I'm going to try to wrap this up really quickly. So over here, we were looking at the whole thing. So the whole time was 4 seconds. But if I'm just looking at the trip up or the trip down, what's the time? 2 seconds. The acceleration is negative 9.8 meters per second squared. Let's see. So, and Vy? So Vy is what at the top? V0 is 19.6. What's Vy? 0. So we can use this formula. V squared y. I'm putting y's after everything now just to indicate we're in the y dimension only. Equals v squared, v0 squared y plus 2a delta y. So this is 0. That's the velocity at the top. The initial y velocity is 19.6 meters per second. Square that. Plus 2 times negative 9.8 meters per second squared times delta y, which is what we're solving for. Bless you. So I just need to square 19.6. Let's see if I can do that. Okay. And then divide it by 2 and divide it by 9.8. Oh, goodness. I think I did something horribly wrong. 19. I should do this on my... I use my phone all the time for this stuff. Divided by 2 divided by 9.8. And I get 19.6.
Yep.
So that's how high it goes. So that would be delta y. We could figure out, or we could fill in a lot of other stuff, but we've answered the question. So when you work on these two problems here, they're on page 8. What we did was a lot like number 2, except this is an easier setup than the way we did it. Number 1, just give your best shot on that. If you don't know how to do these and you struggle, just circle whatever you had trouble with and we'll go over it in class. When's this all due? Monday, or whenever you're here next time. So page 8, number 1 and 2, and then it's the way toward the back. 7